Finally, let's talk about some practical issues in text classification. Now that we've seen the math of naive Bayes, we can turn to some real-world questions. How, in practice, should we build our classifiers in the real world? What classifier you build and what you do depends a lot on what kind of data you have. Let's suppose you have no training data. Well, in that case, the right thing to do is to use manually written rules. So here's a rule for deciding if a document is about grain, let's say. We might say if the word wheat or the word grain is there and doesn't have the word whole or the word bread, so it's not a recipe, then we say this is a grain document. Now, manually written rules are difficult. They need careful crafting. They have to be tuned on development data. And it's very time consuming. It can take days to write the rules for each class. But if we have no training data, this may be the right approach. What if you have very little data? Well, if you have very little data, then naive Bayes is just the algorithm for you. Naive Bayes is what's called a high bias algorithm in machine learning. A high bias algorithm is one that doesn't tend to overfit training data too badly. It sort of trades off variance or generalization to a new test set, so it doesn't overfit too much on a small amount of data. So that's the advantage of naive Bayes. But it's also important to get more data. And you can often find clever ways to get humans to label data for you. And that's an important thing. If you don't have enough data, get more data. There's also various ways that we're not going to talk about so much in this class of semi-supervised training. Find some way to use a small amount of data to help train a larger amount of data, and that's called bootstrapping. And another thing that you might do if you have very little data. If you have a reasonable amount of data, now you might try all the clever classifiers we'll talk about later in the quarter, classifiers like regularized logistic regression or support vector machines. In fact, you can even use decision trees. Decision trees have advantages and disadvantages, but a big advantage of decision trees is they are user interpretable. And that's helpful because people like to be able to modify a rule or hack on a classifier, and it's very easy to modify a decision, much easier to modify your decision tree, add a rule, change a threshold by hand. It's much harder to do that with an SVM or logistic regression. Now, if you have a huge amount of data, well, now you can achieve high accuracy. Although there is a cost. Many classifiers just take a long time. SVMs especially, k-nearest neighbors, can be very slow to train a classifier. Logistic regression can be somewhat better. But really, if you have a huge amount of data, then it may just be efficient to train naive Bayes, which is quite fast. Actually, if you have a very huge amount of data, it may turn out that the classifier may not matter. Here's a result from Brill and Banco on spelling correction, comparing the performance of four different machine learning algorithms, a memory-based learner, Winnow, a perceptron, and naive Bayes, with on a spelling correction task with 1 million words, 10 million words, 100 million, and so on. So a log scale, and where we're measuring how accurate the classifiers are. And you can see that that the difference between the classifiers is much smaller than the difference you get by just adding more data. And in fact, things, depending on how much data you have, the classifiers cross over in their performance curve. So with enough data, it may not matter what classifier you have. So a real-world system in general will combine this kind of automatic classification, whether it's from rules or supervised machine learning, with manual review of uncertain or difficult or new cases. There are some important details for the computation in naive Bayes. One is underflow prevention. So it turns out that multiplying lots of probabilities can result in floating point underflow. We talked about this for language modeling. So since by the definition of logarithm, the log of xy is log of x plus log y, in general, we store our probabilities in the form of logs, and we add them instead of multiply them. So we still have the same formula. Here's the naive Bayes formula expressed now in terms of log probabilities instead of probabilities. It's still an argmax, but now instead of multiplying a probability and a product of likelihoods, we're adding a log probability with a sum of log likelihoods. So now the model is just maximizing, choosing the class that maximizes over some sum of weights. Very simple model. Finally, we're going to want to tweak performance. And domain-specific features for your particular task, domain-specific weights are very important in the performance of real systems. So for example, sometimes we're going to want to collapse terms. Let's say we're dealing with part numbers in some inventory task. Now we might want to collapse all the part numbers together into a part number kind of word, or chemical formula. We might want to have just one named entity called chemical formula. But other kinds of collapsing, such as stemming, generally doesn't help. So you have to know about whether you need to collapse terms or not. It's also very important to upweight. Upweighting is counting a word as if it occurs twice. And so often we upweight title words, or we might upweight the first sentence of each paragraph, or sentences that have words that occurred in the title, we might upweight all the other words in that sentence, and so on. So small ways that can help in tweaking performance. So we've seen a number of practical things that we can do in building up a real-world text classification system.